All right. So, hello everyone, to another FLAN seminar talk. Today we'll hear from Matt Finlayson, a Harvard computer science graduate, now a pre-doctoral researcher at the Aristo team at AI2. And among other things, he works on trying to evaluate the reasoning capabilities of transformers using formal language theory. And today's talk will be on what formal languages can tell us about instruction learning in transformers. Matt, thank you for presenting today. And I'm particularly excited about your work. And so everyone, please welcome Matt, and you can take it from here, Matt.
Great, thank you. I'm also very excited. Thank you for that intro. Great, so I'd also like to actually, before I start, thank Will Merrill for inviting me to speak. I've been kind of following the FLAN group for a while and really have enjoyed the talks here, so I'm excited to be able to present as well. So today I'll be sharing some work that should be of interest to this group, given that it's about formal languages. And in fact, this project was directly inspired by some of my interactions with people here at FLAN. So let's get started. Okay, great. So my talk will pretty much be an overview of the EMNLP paper that I'll be presenting in a few weeks in Abu Dhabi. So I'll be going into more detail here than I'll be able to do at the conference. So it's a great opportunity to ask some questions. And so just feel free to interrupt me if you have questions as we go along. I want to keep this informal and hopefully we can get a good discussion going. So this work is motivated by kind of this recent emergence of an expectation that our language models should be good instruction followers. And by that I mean this expectation that you should be able to go to your favorite large pre-trained language model and just tell it what you want it to do and give it some input, and it'll follow your instructions, produce the desired string conditioned on your instruction. So because instruction following has largely been studied in the natural language domain, it's hard to characterize what types of instructions language models we can follow, what we can expect from them. So to better understand this, we take the approach of developing a synthetic instruction following task. In particular, we use regular languages as a proxy for natural language. So using a synthetic task gives us fine control over our data and allows us to use well-studied properties of regular languages to generate hypotheses about what makes instruction learning hard. So before we go into the details of the study, we're going to do a quick overview of regular languages. This will probably be very elementary to a lot of you, but we'll just do it for completeness. So a language is a set of strings over some alphabet. The regular languages are a family of languages that follow a special definition, which I'll present here. So the first regular language is the empty set. So no strings belong to this language. The next one is the language that only contains the empty string. Next, we have a singleton set containing a length 1 string for each symbol in your alphabet. And then we get to the compositional rules. So regular languages can be composed together to make new languages. And they're closed under set union, meaning that you can take the union of any two regular languages and the resulting language is regular as well. They're also closed under concatenation. So for any two regular languages, the language of strings of the first language concatenated with the strings of the other language is also regular. And lastly, regular languages are closed under the clean star operator. So the clean star of a language indicates zero or more concatenations of strings from that language. So you can show, it's kind of hard to describe, but here's an example to show what I mean by the clean star. So altogether, these are the minimal rules to define the regular languages. As you can see, regular languages are defined in terms of compositions of smaller regular languages all the way down to a handful of atomic languages. So using set notation to describe regular languages can become cumbersome. So regular expressions are kind of a natural and succinct way of getting around the difficulty of using set notation here. So a regular expression, or regex, each symbol in the alphabet represents its own singleton set. So I use this special font here to denote when I'm using a regex. It's a little bit subtle with this font, but hopefully you'll be able to tell the difference. We use a vertical bar to denote set union. We concatenate them together to show concatenation of regular languages. And then we use the star to denote the queen star operator. So pretty straightforward. And then we also use parentheses here to denote the precedence of the operators. So it actually turns out that regular languages are also closed under set complement. So it's possible to add a complement operator to your regular expressions. It's not actually necessary, but adding it makes your regular expressions more succinct sometimes. And it has an important, it's important when defining some properties later on. So we'll actually touch on this again. Okay, so we've gone over regexes, regular languages. Now we can talk a little bit about what we mean by instruction learning. So in contrast to more traditional machine learning paradigms where you, update your model's parameters to a specific task, in instruction learning, you use natural language to describe the task you want, and the model is expected to interpret and implement what you describe. So here's our rival logo, Flan T5. So instruction learning has recently gotten a lot of attention with the release of some new instruction fine-tuned models like the Flan models. So these models were trained on in kind of a multitask setup and are trained with instructions included. So hopefully the idea is that they'll be better at following your instructions when you give them novel tasks. So here, to kind of formalize instruction learning, we can think of instruction learning as learning a higher order function. So this function takes an instruction from some instruction language R and returns a function from inputs X to outputs Y. So for Flan T5, the instruction language that they ambitiously attempt to learn is English. So actually, there might be a multilingual Flan, I'm not sure, but in that case, it would be the instruction language would be the union of all the languages it was trained on. And our goal is to figure out what types of instructions that these types of models can learn. What are the limitations here? So unfortunately for our goal, natural language is extremely complex, which makes it unwieldy, expensive, difficult to use in controlled experiments. Fortunately, on the other hand, we have formal languages, which are much better understood and well studied than natural language. In particular, we can use regular languages as a proxy for natural language. And then this lets us study instruction learning in a highly controlled environment. So to make this formulation explicit, we use regular expressions as our instruction language. And then we expect our model, given a regular expression and an input string X, to output true if the string belongs to the language expressed by the regex, otherwise false. So we have this kind of natural mapping from regexes to instruction learning. So just to note, this is different from kind of past uses of regexes to investigate transformers, say, because usually we use regexes as we have a model that's learning a single regular expression or a single regular language. Here we're learning an interpreter of regular languages. So you can give it an arbitrary regex and expect it to do that regex recognition problem. Great, so what does this look like? Well, we build a data set with a training set and a testing set. Each instance in the data set has an instruction regex, an input string, and a label, true or false. The training and test sets have disjoint sets of regexes, but they're drawn from the same distribution. So none of the test time regexes will have been seen during training time. In fact, none of the test languages either have been seen during training time. Now we're going to get into a little bit of detail about how we generate these data sets, because sampling formal languages is kind of a non-trivial task. So naively sampling regular expressions results in a huge amount of redundancy, and especially bias towards larger regexes, larger input strings, just because these things grow exponentially with size. So for this reason, we introduce a number of criteria for our sampling algorithm. So because the number of regexes increases exponentially with the size of the regex, a naive sample would produce mostly large regexes. And so to mitigate this, we limit the number of regexes from each size up to a maximum size. So we go up to depth six compositions. Similarly, the number of strings also increases exponentially for the length of the string. And a naive sample would mostly produce long strings. So again, we limit the number of strings from each length up to some maximum length. We actually go up to length 15 for the strings. And then where possible, we make sure we sample the same number of positive and negative examples for each regex. Not always possible because some regexes might only have 1 or 2 positive or 1 or 2 negative strings. And then because the same regular language can be expressed in many different ways, we choose a unique regex for each language and enforce that the chosen regex is the shortest possible representation of that language. So I'm not going to go into too much detail here on the sampling algorithm, but we can actually come back to this if people are curious to see how we enforce these criteria. Great, so now we're going to go over how we use our regex dataset to study instruction learning. So we begin by training a T5 based model called Byte on the regex training set. So it's based on T5, but it uses, instead of sub-word tokenization, it uses character level tokenization, which is important because our data is highly synthetic. A sub-word tokenizer would probably hurt performance here. It'd group things together that shouldn't be grouped. So we wanted to give it the best chance possible. We elect not to use raw accuracy to evaluate our models because it can be misleading. So it might show the model is doing very well when it's actually missing some important edge cases for one regex or another. So instead, we're interested in the proportion of instructions or regexes that the model is able to master. So our metric we call performance at n, so as in performance at 90, performance at 80, measures the proportion of instructions that are at least 90% accurate. So we can adjust the difficulty by making n bigger or smaller. Great. So we've built our regex recognition task. We've trained our model. Let's get into the results. So what types of instructions does our model struggle with? We start with what we call language level attributes. So these are attributes of regular languages themselves. Later on, we'll get into regex specific and input specific attributes as well. So first, let's focus on a subclass of regular languages, the star-free regular languages. A regular language is star-free if it can be expressed without a clean star, if you allow using the complement operator. So as an example, A star is star-free because it can be expressed as the complement of the language of strings containing Bs. So here we have, this represents the language of strings containing Bs, and this represents, and so we just take the complement of that. And so it's any string without Bs. So on the other hand, A star is not star-free. I'm not going to present a proof here. But just something to note is that recognizing strings of AA stars requires keeping track of whether there are an even or odd number of A's in a string. So the class of non-star-free languages can be characterized as the class of languages that require modular counting. So it turns out that the star-free languages are, in general, harder for our language model. This plot shows that the mean accuracy for non-star-free languages is lower than for the star-free ones. Furthermore, we see that the model only gets above 90% accuracy on 72% of the non-star-free languages compared to 92% of star-free languages. So we take this to indicate that we should expect models to struggle with following instructions that require some type of modular counting. So this has been hypothesized in prior work, but here we show that this issue arises specifically in the instruction learning setup and with a much larger transformer than what's been used in the past to test this type of thing. We also look at the size of the languages. So by size, I mean the number of strings in the language. It turns out that the more strings in the language, the harder it is for the model to learn from the regex instruction. So from this, we conjectured that more ambiguous instructions, ones that might be executed in multiple ways, like a language with many strings, could be harder for transformer models. Now we look at some expression level attributes. Oh, sorry, I see a hand.
Yeah, very interesting. I was a little confused about the size of the language. Many of these are infinite.
Oh yes, that's a great question. Yes, so we make a kind of a simplifying. So because we're only testing strings up to length 15, we use the number of strings up to length 15 that are in the language as kind of a proxy for size, because you're right. These languages, a lot of these are infinite.
Got it. Thanks.
Marco, was that the same question, or is that?
That was my exact question. Yeah.
Okay, yeah, that's a good catch. I forgot about that assumption to put that in here.
Another question is the small and large here refer to the size of the transformer, right? Not the size of the language. Or so what are small and large?
This is. Oh no, this is sorry. This doesn't have a lot of tick marks on it, but this is the size of the language. So the number of strings that are in the language. Sorry, I didn't quite get that.
In the table, what are small and large?
Oh, sorry. So this is less than 64 strings in the language, and this is greater than 64 strings in the language.
I see. Okay, so you're just breaking that plot down in a different. Cool. Got it. Thanks.
Yeah. So yeah, initially we just kind of chose a cutoff, but then we actually went back and made a more descriptive plot to show that it kind of monotonically almost monotonically goes down with size. Great. So next we get into some expression level attributes. So these are attributes that have to do with the actual instruction language, the regexes, rather than the languages that they represent. So as an example, we'll talk about composition. So, sorry, excuse me. Regexes are composed of smaller regexes. So we look at the effect of the number of compositions in a regex on how hard it is as an instruction. So here the number of compositions is 4 because 4 compositional operators are used to construct this regex. We find that more composed regexes are slightly harder for our model. So the plot here shows that the mean accuracy decreases as the number of compositions increases. It's important to note, though, that this effect is smaller compared to the previous 2 that we looked at. Another expression level attribute that we look at is what we call unobserved local structures. So this is inspired by some prior work that does some really cool stuff showing that unobserved local structures in examples are what make compositional generalization hard. So because this is a very compositional task, we kind of assume that, oh, so maybe if there are unseen substructures at test time within a regex, that regex should be harder. So we decide to test whether this is the case in our setting. So to do this, we extract all the regexes and their sub-expressions from the data set. So as an example, here are the sub-expressions of this regex. We then classify all of the test regexes by whether or not they contain sub-expressions that were in the training set. The idea here is that perhaps regexes are harder if they contain a sub-expression that wasn't in the training set. So looking at our results, at first it actually appears that regexes with unseen structures are indeed harder. But this is only the case when you look at all of the regexes together. It turns out when you separate out the regexes by their size, by the number of compositions, the effect disappears and even reverses in some cases. So this is kind of an example of Simpson's paradox, where a relationship appears when you look at the data in aggregate, but when you control for another variable, the effect might even reverse. So we don't find that this is has a major effect on the difficulty of the regular expression. So it's kind of interesting to me that we looked at language level attributes and kind of more expression level attributes. So these could be thought of as like underlying task attributes versus the syntax of your instruction language. And what we found is that the underlying task has a much bigger impact on the hardness of the instruction than simply the syntax, the compositionality of the instruction that was given. We're going to go over one last attribute that we look at, and this is a instance level attribute, meaning it doesn't just depend on the regex or the language underlying it, but the actual test string instance. So for each language that we test, we construct a minimal DFA and track the number of states that are visited while recognizing strings. So it turns out the more states that are visited while recognizing the string, the less likely the model is to get the instance right. So intuitively, this kind of corresponds to keeping track of the context of the string and in order to determine the correct next state. I see a question.
Yeah. Do you mean the number of unique states that are visited? Because like the number
Yes,
of
sorry.
states that you visit, okay, is like So not the length of the string.
Not the length of the string, the number of unique states that are visited. That's right. It's a good good point. Great. So yes, Dana.
So I'm a little puzzled as to why it stops at 6. Nothing visited more than 6 different states. The strings are 15, right?
Yeah, so the length of the strings only goes up to 15, and because we construct the minimal DFA, yeah, we don't actually see. I think there were a very small number that actually went above 6 to 7, but I was actually surprised too how few unique states are visited in the DFA.
So how many states were in the largest DFA in your construction?
I don't have that number currently.
Because
I could look that up.
in principle, a regular expression can blow up exponentially when you turn it into a DFA. So the DFAs could be quite a bit larger than the expressions, right?
Yes, that is correct.
But that didn't so much happen here, or?
You picked the smallest. What was it? How did you pick the regular expressions, like the canonical form for the regular expression? It was the smallest regex or the smallest DFA
the smallest,
then state eliminator?
So the smallest regex, like the fewest number of compositional operators, and we only went up to 6 compositional operators. Yeah, this is one of the things that I don't have great intuition about when it comes to regexes. But yeah, often the DFAs that we constructed were quite small.
Oh, cool. Right. Thank you.
Thank you for your question. So, yes, so intuitively, this having more execution states, having more unique states visited while recognizing the string, corresponds to taking into account more of kind of the context of how you got to a certain state, keeping track of what state you're in while recognizing the string. So we hypothesized that in the future, looking into kind of a more natural language setting, we might see that transformers have more difficulty following instructions that require kind of closely tracking the context. Great, so based on our findings in the previous section, we found a few attributes that seem to make instruction learning hard. But it's possible that the model does badly on these types of regex solely because they were, say, underrepresented in the training data. So to make sure that this isn't the case, we construct a challenging version of our data set and retrain our model only on these hard examples. So based on our findings in the previous section, we choose to include only star-free large languages and examples with a higher number of execution states. So let's look at what happens when we train on our hard data set. Just a quick note, this refers to the exploration set, the first data set that we created. And then hard is the one that's kind of filtered only for the hard regular expressions. So what happens is we see that the model is not able to recover nearly its original performance on the data set. So whereas before we got above 90% accuracy on almost 90% of the regular expressions, here we only get 65% getting above 90% accuracy. Furthermore, we see that generalizing back to the easier expressions from the exploration set is even worse than generalizing from the easier ones to the hard ones. So just kind of overall, we see that generalization here to different distributions of regexes is very difficult for our model. Yeah, so I think the most important result here is these attributes that we identify indeed seem to kind of be hard by themselves. It's not just because they're underrepresented in the training data, it's because they're actually difficult for this model. All right, so we've arrived at the end, and so let's do a quick summary. So we're able to use regexes to study instruction learning, and the advantage here is that regexes make for a highly controlled study, avoiding a lot of the complexity and ambiguity of natural language. And we're able to identify several attributes that make instruction learning hard for at least our T5-based model. Though we identify a few, there are probably a lot more factors out there that make instruction learning hard. Not all of the ones that were classified as easy were indeed easy for the model. So we've released our data sets to the public, and I'm excited to see what future research finds on this type of task. So thank you all for coming to my talk, and I'd love to hear any questions if you have any. Thank you for the silent applause. I see it. Great. It seems. Oh.
So since
Marco?
Oh, sorry, Marco, go ahead.
I don't think I can hear you. Can other people
No, Marco,
hear?
I also can't hear you. I think your mic is off. Marco said that his headphones died and his mic isn't working, but he'll try to fix it.
It's unfortunate.
Okay, but we'll wait for till the recording is up. Okay, maybe I just end the recording and then here. Thank you for your talk.